All right, so now we're going to talk about how did a guy named Niels Bohr come up with what we call the Bohr model using the idea of light as a wave. So the first thing you got to understand is what's called the photoelectric effect. And the idea of photoelectric effect is when electrons are excited by light or by, in this case, light. What happens is the electrons gain energy, and that energy pushes those electrons into an excited state. So it can push these electrons to be ejected off the metal, and so solar calculators work this way. This is how solar calculators get energy. All right, so now let's talk about what ground state versus excited state. And so in this case, a ground state, so an electron at a ground state is an electron that basically is not excited. It has its lowest amount of energy, and so we call this a ground state. So you can say this is a ground state. So let's just imagine I have an electron hanging out here. It's at ground state. Once you add something like heat electricity, I should have added, or light in the photoelectric effect. What happens is, so like let's say, I'm just going to say red's my energy. So if I add this energy, what happens is the electron gets excited because it now has energy, so it gets boosted up into an excited state. So an excited state, it just means we added energy to this electron. Okay? All right, so how does this work? So very simply, what happens is you have an electron. So let's say we have an electron. So we call this ground state. And then we have the excited state. And then we have back to ground. All right, so let's imagine we have an electron. And let's say this electron is hanging out at a ground state. So I'm going to call this ground state. All of a sudden we have light, or a photon, hit. So this is some type of energy. Once that energy arrives, you have an excited electron. So the electron now, so this is where ground state was. So the electron jumps, and so now it's at the excited state. So this electron now has energy. So it's at its excited state. But at some point, this electron wants to return to its ground state. And so at some point, the electron, here's the excited state, the electron will return back to its ground state. But here's the thing. The energy has to go somewhere. So what I mean by that is like, before the electron can go back to its lowest energy state, or what's called the ground state, it has to remove that energy. And so how it removes the energy is it actually removes it by giving off light. Let me do it in a different color. So the electron, as it's going back to its ground state, it gives off light. And light, in terms of like some type of photon. And remember, light is given off as a wave, and we see light as different colors, right? So so the light it gives off is a wave. Now, if we look at light, or if you look at the light that's given off and you look through a spectrum or some kind of diffraction gradient, you can actually see the exact waves it gives off. So it can give off several waves, but what I want you to get is that wave has a certain wavelength. That wave of light has a certain wavelength, right? And so the wavelength determines the color. So here I have orange, so it might give off an orange color. If it has a longer wavelength, it might be more towards red. If it has a shorter wavelength, it'll be more towards blue, indigo, and violet. So what I want you to see is the color that it gives off actually tells you the amount of energy that it gives. And so let's take a look at our next things. But just to recap, ground state, the electron's hanging out, all of a sudden it requires energy. It goes up to an excited state. At some point it wants to return to its ground state, but in order to return it has to give off energy. It gives off energy as light, and depending on the amount of energy it gives off, it could be a high energy wave that has a really short wavelength, so it might be violets or blue or indigo. If it's a little amount of energy it wants to give, it's going to be it might be more towards the red or the oranges that has a longer wavelength but lower energy. Okay? All right, so let's look at a hydrogen. When hydrogen is excited, when it returns to ground state, it gives off these four. It gives off these four bands of light, or of these four wavelengths. That's what you see. And so what happens is when the electron is excited, what happens is what they find out is in hydrogen there's actually four different. So here's your ground state, but the electron can actually go to four different states. So it could go, that we can see. So it could go to this excited state, right? It can go to this excited state, this, or this. So there's four different excited states it can go to. So the electron can go to here. It could go to here when it's excited. So let's say it got more energy. It can go to here if it got even more energy, or it can go all the way to here, right? Now remember what we just said, it wants to return back to its ground state. So let's take this very top one. If the electron takes one big jump and returns back to its ground state, what you'll notice is since this is the highest, this gives off the most energy. So it's going to release the most energy. Well, what wavelength gives off the most energy? So what I'm saying is the electron that got up to the highest energy level gave off the most energy. That energy we see as violet. Remember, violet has a shorter wavelength, it therefore has a longer, a larger energy. And so, what about this one that just goes here and then it returns back? Well, this is the shortest jump, so this is the least amount of energy, right? Least amount of energy means longer wavelength, shorter frequency, and so it'll be right there, right? And so you can see, but what I want you to get from this is, when Bohr saw, oh, there was multiple bands, that told him, oh, there are these multiple levels or energy states that the electron on hydrogen can go to. And so therefore, around the nucleus in the electron cloud, there must be these states. And so he called these states or energy levels, he just made them into rings, almost like a planet. So here's ring 1, like this is your first energy level, and then here's your second energy level, and here would be your third energy level, and here would be your fourth energy level, right? And so the electron could jump from here to here, or it could jump from here to here, or it could jump from here to here, right? And the fact that they can make these discrete jumps, means that there must be these energy levels that these electrons belong in. Bohr modeled these electrons as rings around, the energy levels as rings around the nucleus, okay? All right, so Bohr's model is there's a protons, neutrons in the nucleus, kind of like what Rutherford said, but he found that electrons are found in energy levels that circle the nucleus. Electrons fill the lowest energy level. The maximum number of electrons per energy level equals 2n squared, where n equals the energy level. For example, in the first energy level, so here's the first energy level, n equals 1, right? Energy level is 1. So the maximum number of electrons that can be found there is 2n squared. So that is 1 squared. So that equals 2. What about the second level, energy level, or second ring? Well, 2n squared, 2 times 2 squared gives you 8, right? 4 times 2 is 8, and so on. So n equals 3. 2n squared, this would be 2 times 3 squared, this would be 18, okay? All right, so let's do a couple examples of Bohr models. So we're looking at boron 11. So the first thing I do is I determine the number of protons, neutrons, electrons. Boron, according to your periodic table, should have 5 protons, I believe. It should be have atomic number 5. That's right. So it has 5 protons, and then since it has 11. The mass number 11, it should have, I'm sorry, that's 5, right? So this is 5. The neutrons, therefore, should be 6, and then the electrons, since it's neutral, should be 5. All right, so to draw a Bohr model, we need the nucleus first, so I usually put 5 protons, 6 neutrons in the middle. Then I draw my first, so this is my first row, or my first energy level. If you remember previously, in the first energy level, you can only fit 2 protons. I put my protons as like marks. Some people put like dots. It's up to you. It doesn't matter. I put marks because it's easier for me to see. So remember, it wants to fill in the lowest energy level. So the first energy level is the lowest. The second energy level is the second lowest. I used up 2 electrons. I have 3 remaining because I have a total of 5 electrons. So in my second energy level, remember, 2n squared, so I can fit up to 8. Now, however, I used up 2, so I have 3 left over, so I just put 1, 2, and 3. I have 5 total electrons. 2 of them are fill up the first energy level. That can only fit 2. Then the second energy level has 3 more for a total of 5. Try phosphorus on you, see how you do. So for phosphorus has 15 protons. Neutrons would be 16. 15 plus 16 gives you 31. The electrons is 15. Let's do the Bohr model. So the Bohr model in this case, my protons and neutrons, 16 neutrons. So I can fit 15 electrons. The first one is 2. The second one we talked about is 8. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 10 total electrons. I still have 5 remaining. I can fit up to, in my third energy level, I can fit up to, let's see, what's 2 times 3 squared? That's going to be 9 times 2 is 18, right? So I can fit up to 18. I just need to fit 5 more. 1, 2, 3, 4, 5, and that's it. Okay? And that's it. I have more practice for you, and I have a key as well.